Okay, so can people online hear us? Give some indication.
Perfect.
All right, can you online hear us? Oh yeah,
Okay.
yes. Okay, great, no problem. Okay, so great. So sorry for a little bit delay. So it's my great pleasure to introduce to you today's speaker, Jiaming. So he's from NVIDIA Research. So basically, previously he has done his PhD with Stefano Amo, the group that works on a lot of things on this, and he has some very notable research on this line of diffusion models, including DDRM, which is like the very first acceleration sampling methods that inspire a lot of later on the developments for all these kind of public diffusion models that you can see now. So yeah, so it's great to have you here. So then take it away.
Okay, all right. Yeah, thanks, Yingjian, for the nice introduction. So I'm Jiaming, and today I'm going to talk about diffusion models for inverse problem. To start with, let me first show some results from NVIDIA that shows how diffusion models are very powerful generative models. And specifically in the past year, there has been an explosive growth for image generators in diffusion models. So for example, you can see in here, there are several images with very detailed text descriptions, and these are all powered by a diffusion model to generate images of various levels of detail. And even in the past year, there has been a lot of steady progress. So for example, here we have this prompt that says, golden retriever wearing a green shirt has text setting in NVIDIA rocks. So basically, DALL-E 2 is a model from early 2022. Stable Diffusion was a model from mid 2022. And our model comes from later 2022. And you can see actually it gets the text prompt correct. And it's mostly, we can see the progress of this diffusion model training become very accelerated. And similarly, you can get a style reference plus text conditioning to get different types of generation as well. As well as combining words and segmentation maps to generate images that are not only describe the image but also describe the location of certain objects in detail. So for example, in this case, we have specified where is the full moon and where is the boat, even when the text prompt does not specify the exact locations. And of course, by training on a large data set, we are able to generate images that are of different styles as well. So this is just by changing the text prompt of the language model. But today we are not actually talking about how you train next generation text to image model, because I know it's very tricky for academia researchers to do that. So today I'm going to talk about a slightly different topic about basically how you can use these powerful diffusion models as priors for other interesting downstream applications. And more specifically, here I want to mostly talk about applications in inverse problems. So for example, a setting here is that we want to perform this task, that we want to do a denoising and super resolve this image. And as you can see, this face image is low resolution and very noisy. So the high level idea between a Bayesian-based or a plug-and-play-based method is that you are starting with a prior. So for example, here my prior is a generative model that generates 2 images. And I can combine it with the likelihood function. So basically, this likelihood function will basically tell us how likely it is from this high resolution image to downsample and add noise to get this low resolution noisy image that we observe. So of course, the upper image is more likely to downsample and generate this type of image than the bottom one. And basically, by combining the prior and likelihood, we have a method that basically give us the posterior, which is like the desired solution as of here. Similarly, we can do the same thing with the different tasks. So for example, here is an impinging task where we want to recover the masked region of a particular image. And we have the same prior, but we change the likelihood into this masking defined by masking, and we get the different solution, which is based on the different posterior. And in this plug and play nature, the prior is fixed, and in different tasks we plug in a different likelihood function, and this will give us a different procedure. So people have been using these type of ideas for in generative modeling. For example, people have used variation autoencoders or generative adversarial networks to serve as priors. But they have, first of all, they are they're studying more than diffusion models, even though they have like worse sample quality. But on the other hand, diffusion models have their own challenges. Unlike VAs and GANs, where you can do sampling or likelihood evaluation in like one step, in diffusion models, you need multiple iterations to even evaluate the likelihood or draw a sample from it. So like plugging in this plug and play framework with diffusion models has its own challenges. And today our topic is mostly asking how we can use more generic diffusion models as a tool for solving these different general inverse problems. And I believe this is a topic that has a lot of interest in both in like academic research and industry research. So just as a highlight, so before we delve into details, here are some results. So for example, here is a task where we have a JPEG restoration task plus some mask. And you can see the input is relatively corrupted with JPEG artifacts, and our output is able to recover this image without, that's relatively realistic. And if you want to train a conditional diffusion model on top of this, then you have to train on both JPEG restoration task and the impinging task. And this will like be a bit tricky even for large companies. Similarly, we can just combine these tasks together. So for example, here we combine JPEG and super resolution, and we have another task, but the diffusion model can still recover this. And same, we can just mash everything together. It can be solved that way. So our roadmap today is like this. So first, I will give an overview of DDRM. This is mostly to have a brief discussion over what diffusion model is, and this is used as context for the following works. And next, I'm going to talk about a work called the Denoising Diffusion Restoration Models, which tries to solve noisy linear inverse problems on images with like very good efficiency. And this is accepted in Europe last year. And third, I'm going to talk about a recent work called the PhysDiff, where we apply the idea of the earlier restoration models work to a task that is not necessarily on images, but it's on human motion. And finally, I'm going to talk about a recent work that's accepted to ICLR 2023 called Pseudoinverse-guided Diffusion Models. And we want to close the gap of the plug-and-play methods to domain-specific methods. So a very quick overview of denoising diffusion models. So basically, we have a clean image that we call here as X0, and we add some amount of Gaussian noise. And here, for example, we add Gaussian noise that has like standard deviation of a sigma t for every dimension, and every dimension we add Gaussian noise independently. So after we get this image, we call this image xt, and the task we have here is basically we want to predict x0 from xt. And you can see from the top L2 loss, where we have a denoising model, now we denote as D, that takes in the noisy image xt, as well as the current noise level, so sigma t, to do this denoising. So denoising autoencoders are not very strange to perhaps the audience here, but what's interesting about the denoising diffusion perspective is that instead of training one denoising autoencoder at one noise level, you train a series of different models, and these models can have like initialized with small noise, initialized with middle noise, or like very large noise. So basically, all of these different models, you train it with this, L2 objectives, except that you have a slightly different input. So the high-level idea of a denoising diffusion model is that it wants to reverse the diffusion process. So basically first we have to define a forward diffusion process, which starts from the data distribution, and you gradually add Gaussian noise to to this image, for example. And by adding more and more noise, your image will obviously become more and more noisy. And as you add like almost the amount of noise is infinite standard deviation, then you essentially remove all the signal that was originally in the data, and it was mostly just a Gaussian noise. So the denoising diffusion model basically tries to revert this process. So we start with something that is essentially Gaussian noise, and we try to use our denoiser to denoise the noisy Gaussian noise. So here, at each step, we have an iterative process, and each step we are using the denoiser at a certain noise level, and we have a particular update procedure that gradually denoises this noisy image. And essentially, we want to repeat this process for multiple steps and reach a final clean sample. Without having to spend a lot of time to get into the actual details, this is also connected to denoising score matching. So basically, we have this equation on the right showing that the optimal denoiser that you learn is like equivalent to having this score function. The score function is the gradient of the log probability of the perturbed distribution. So this is the distribution of the data, but perturbed with the Gaussian noise. And another perspective of this sampling procedure is that you can think of it as solving kind of like a complex stochastic differential equation or ordinary differential equation. So you start with this PT of xt on the left, which is just a Gaussian, and you have this procedure that transforms this Gaussian into the desired complex distribution that you want here. But to set up things for later topics, I have to first introduce the work that I did on denoising diffusion implicit models. So you can think of it as kind of like the first order solver of the previously very difficult like score SD, and it's the actual derivation of it will be very complicated. Concerns topics like variational inference, focal Planck equation, or Schrodinger bridges. So today, to keep things simple, I'm going to only describe the idea driven from the place where your distribution only has one data point. So if any method works on generative distributions, it has to work on one data point. So I'm trying to do the reverse. I'm going to explain the idea of DDRM just for one data point. But if you take it deeper, it also works for generative distributions. So the high level idea is like this. So let's start with a sample xt, which is basically x naught plus some Gaussian noise, and the Gaussian noise has standard deviation of sigma t. And we want to take one update to get to the next smaller noise level, and this is described as xt minus 1. And this is basically you can think of it as just the x naught, the signal. Anyone asking a question?
Also
All right. Yeah. So then we are trying to do an update which goes to xt minus 1, which is the signal x naught plus sigma t minus 1 times the noise. So we always assume that sigma t is bigger than sigma t minus 1. So that becomes a denoising process. So in this first case, we are basically trying to argue that in the one data point scenario, you can decompose the signal and the noise in a linear fashion. The second fact that we have from the oversimplification assumption of one data point in this distribution is that your denoiser output is always going to be this one data point x naught. So because basically you add Gaussian noise to this one data point, and the optimal solution will be the mean of the corresponding Gaussian, which is exactly just the one data point you get. And last but not least, we will use the fact that summing IID Gaussian distributions also will give you a Gaussian distribution. So for example, if you have a Gaussian distribution with variance a squared, and then you plus it with something that's variance b squared, you will get a Gaussian with variance a squared plus b squared. So to get DDRM, which is we treat it as a first order solver for some like SD. The high level idea is basically just we want to linearly combine our input, which is xt, our denoised output from the diffusion model, as well as some additional random Gaussian noise to get the next iteration xt minus 1. So here you can see from the diagram, we start with input xt, we try to denoise with the diffusion model and get this denoise solution, and we have a linear combination between the three terms. So how exactly is the linear combination done? So we want to basically get coefficients of these three terms. So let's use A for the coefficient on top of the input, B for the coefficients for the denoise output, and C for the coefficients for the random Gaussian noise. And combining these linearly, I expect to get something that is the same distribution from xt minus 1. So the first condition is basically we want to match the noise level. So basically, before we have the input, which is standard deviation sigma t, we want to convert it into standard deviation sigma t minus 1. So basically, we have the input which has standard deviation. The variance is a times sigma t squared. And then the Gaussian noise also has a variance of c squared. So these two will sum up, should give you the sigma t minus 1 squared. And the condition 2 is basically that you need to keep the original signal coefficient also like stable. So basically here A is the input, which has a signal coefficient 1, and B is the output, which also has a signal coefficient of 1. So as a result, A plus B needs to be equal to 1. So basically, we have 3 variables, and there are 2 equations. And naturally, there is a 1 degree of freedom that we can choose here. So for example, we can choose a different C. And using the first condition, we can get the corresponding A. And then using the second condition, we can get the corresponding B. So what C means is basically, it's like the amount of stochasticity in the process. So if C is larger, then each update will have more stochasticity, and vice versa. So basically, this is kind of like the set of this series of equations that updates that we derive in the DDRM paper. So for simplicity in this, we will omit these Gaussian noise graphs in the later figures. But what's interesting about DDRM is that basically the ODE solver, which corresponds to the case, C equals 0 is quite efficient, and it often gives you very good results in 20 or to 100 iterations. And you can see on this graph, each column is the same random C that was initialized in the Gaussian distribution. And on each row is running the DDRM algorithm for 10 steps up to 100 steps. So here we're just saying that the method can actually get to pretty fast conversions with just like, say, 20 to 50 steps. And we are actually going to use this as like a means to derive faster algorithms for inverse problems. So now let's talk about the first work on using diffusion models for inverse problems, which is denoising diffusion restoration models. And this is work done by Bakshat, who's the first author here, and he's a PhD student in Technia. Michael, who's Bakshat's advisor, Stefano, my advisor, and myself. So in the setting of linear inverse problems, this is actually, despite it sounds very simple, it's actually, there's a lot of image-related problems that are like purely linear. So for example, we can define a linear inverse problem as follows. So given clean input x0, we observe this input in a noisy fashion. So the way we observe this is that we multiply x0 by a matrix H, which is called the degradation matrix, and we add some Gaussian noise, potentially Gaussian noise with a standard deviation of sigma y. And this will give us the noisy observation y. So some examples are as follows. So for example, in super resolution, H would be some kind of a downsampling operator that is linear. In painting, this is basically the masking operation. And in deblurring, this is just adding some type of blur, such as a Gaussian blur or uniform blur. And as you can see, this corresponds to many different image processing problems, but it also has a lot of different, there are also a lot of different problems, for example, in medical applications, such as MRI or CT, where these are also linear inverse problems. So before we go to the actual detail, we can first show some results to show how good it is. So you can see that in the top row are the observations or the inputs, and at the bottom row are the outputs from our method. And you can see that our method is able to handle both these linear corruptions as well as noise at the same time. And we also know that this method does not only apply to natural images, but it also applies to medical images, as well as different domains, such as astronomy, as well as different domains and images, such as speech and audio synthesis. So to describe the high-level idea of what we do here, we first consider the easiest case. And this case has been also discussed in prior works again. So this is the case of this noiseless in-painting. So specifically, we observe a particular y, and this y is like a mask image. And mathematically, you can think of H as a diagonal matrix with terms of zeros and ones. So for the zeros, you just don't observe them. And for ones, you observe them exactly. And Z here has zero noise. So the intuition of our method in this case is like this. So first we have some random Gaussian noise, and we are trying to use our diffusion model to do denoising. And obviously, at this stage, we haven't used the information of y. So these two processes are kind of independent. So one way to enforce this information about y is to simply just do a linear combination. So I basically take the denoise result and I overwrite whatever that we observe using the information from y. So then we will get this updated denoise result. So basically, in this new image, all the observed pixels have been overwritten by the ones that we get from y. And we will use this to construct our linear combination that we described earlier with the DDRM. And so basically, now the input will be xt, which is the input, the updated denoise result, and some Gaussian noise that I haven't drawn here. And I will get the next iteration of xt minus 1. And this will bring the sampling process closer to being consistent with the desired conditions y. And by running this algorithm repeatedly, we can just get samples that are less and less noisy, but also are closer to the desired conditions. And finally, as we goes to noise level 0, hopefully we will get something that is a realistic image, but also satisfies the conditions that we enforce on top of it. So mathematically speaking, we can think of updating this denoise result as combining information of y and combining the information from this denoise output, which we call xt hat here. This is a linear procedure, of course. And then we also have the linear combination that we described earlier in the DDRM case. And this is basically just a linear combination with certain coefficients. And you can see that we now have two linear combinations here, but we can also just treat the entire thing as kind of like a linear combination black box. And this black box takes in 4 inputs. So the first input is the original xt. The second input is the denoise result, xt hat. The third input is the observation y. And the fourth input is the random Gaussian noise that I haven't drawn here. So yeah, I'll describe how to exactly do this slightly later. But a second case that is slightly more difficult is the case of a noisy in painting. So in this case, we not only observe masked images y, but on every dimension of observed y, we have a certain amount of Gaussian noise. And we assume that this is known with a Gaussian standard deviation of sigma y. The H is still a diagonal matrix with zeros and ones. And we will try to consider two different scenarios. So the first scenario is the case where our current noise level at this diffusion model is quite large. So we are a bit uncertain about what the image should be. And in this case, giving the noisy y actually will provide some information of where to guide it, even though it is noisy. So at a high level, you can think of it, our update will still be this linear combination box, but with considering how the sigma y works, because of course we can't just use the original update. Otherwise, we will just get a noisy image at the end. And I will go to how you evaluate this linear combination in a bit. So in the second case, after we have done a series of denoising and we have injected some information using this observation y, then we will reach a point where our noise level is relatively small. So for example, here, given this xt, we are pretty sure what the final image would be. And in this case, the information about y is a bit more noisy. So more specifically, it is more noisy than the noise level at the next step. So in this case, basically want to not use this noise observation, because even if we use it, we are at the noise level that using it does not actually help us that much. So in this case, we will just do a linear combination, but with a different case, which we don't actually consider the observations exactly. Yeah.
Okay, can I ask a question? Okay, so it seems to me for a given t,
yeah,
the procedure from xt to xt minus 1, it feels like getting things from posterior, right? It feels like xt is kind of like this round's prior proposal, and you use this linear combination to somehow correct it, simulating a posterior process, right?
Yes.
Okay, the thing I'm a little bit confused about, right? So now xt minus 1 is your sort of like next proposal, but from posterior, right? So but you're at the beginning, you basically say about inverse probability is basically you propose things from prior and then get correction from posterior, right? So how would these things go around for multiple times, given that xt minus 1 is in some sense like a posterior sample?
I guess basically the prior will be something that's in the diffusion model. And the likelihood term, you can think of it as kind of using y to help you correct the what samples you get from prior. So I guess in that sense, you combine them as a posterior. But I guess it's slightly different in the sense that like how traditionally you would get the posterior by like longitudinal dynamics or things like that. So because we also have like efficiency, the algorithm efficiency in mind. So here we are mostly just trying to describe a heuristic that works pretty well. In the paper, we actually have some description of like how this corresponds to like a variational solution to the posterior, but it's too complicated. And when I explain to others, in other talks, nobody understands it.
So probably I can understand this linear combination part as in some sense like an implicit way to define the likelihood you want, and then you are doing some iterative search in the posterior case. So
the exact way we motivated our work in the paper was that we have this conditioning sampling algorithm, so P of X given Y, and we are basically constructing a diffusion process that's also conditioned on Y, the forward diffusion process, like Q of X given Y. So we construct this Q of X given Y that satisfies certain desirable properties. And basically from there, we can get the reverse of that, also using this prior diffusion model. And basically we have some statements showing that the objective function, it makes sense. And you can actually use prior models to get that.
So it's a very good question. I mean, in this case, because Y given X0 is, if you think about likelihood, the posterior is exact, right? So you can get like, if you have a prior on X0, then P of X0 given Y is exact. And the update would be something similar to you showed some like there is the pseudo-inverse term, and then there is the regularizer. So how is it related to an iterative Bayesian update in some sense? Like you just keep updating the posterior of X0?
Yes, definitely. So I think there's a lot of like connections of this method to existing methods of plug and play methods in like using denoisers, for example, such as regularizing by denoising. And I think there are a lot of connections, and I think people are also trying to explore these. But I think what's interesting about the diffusion models was that it has this, annealing procedure of the energy of different noise levels. And in that case, we actually leveraged the, fast sampling algorithms such as the DDRM to give us, accelerated updates instead of having to, tune for specific like longevity steps or like gradient descent steps. And I think that's actually what's the most interesting about like using a diffusion models in this context.
So can I just check? So in this problem, is sigma y known or unknown?
So yes, in this case, sigma y is known. In practical cases, you can usually estimate sigma y. Sigma y does not have to be same across the same dimension. So you can have like different for different dimensions. I think you can have different sigma y. Yeah. All right. So basically, on the high level, if my sigma y is larger than my current noise level, I'm just going to ignore my observation because this is currently just too noisy for my use. So in that case, I'm just going to run DDRM as if I'm just doing unconditional sampling. In the other case, I'm going to use this information about the noisy y. However, the problem is that the y is noisy, so we can't just use it as is for the noise. Identical to the noiseless case. So basically, our high-level idea is that we want to perform similar linear projection, but on this sample that we call the noisy denoise. So the idea of this is basically that we first get a denoise sample from XT, which is from the diffusion model, and then we will add back some Gaussian noise. But what's different is that here, the magnitude of the Gaussian noise that we add back is exactly equal to sigma y. So this is not tied to the noise level. And essentially, we want to combine the noisy denoise sample, which has a signal coefficient of 1 and the noise coefficient of the sigma y, with the noisy observations. And in the noisy observations, we also have this signal coefficient of 1, and the noise standard deviation is sigma 1. So basically, by combining these two, we have an object that also has like a signal coefficient of 1 and the noise coefficient of sigma 1. So in this case, we just use this, we try to derive a slightly different linear projection on the noisy denoise samples. So now the input takes, again, 3 inputs. So xt, which is the same, which is just the input of our algorithm. Now we have this xt tilde, which is this, sample that we combine with the noisy observation. This is the only thing that's changed, and as well as the Gaussian noise that we haven't drawn here. And we have only changed the second term in this update. But this requires us to get all right.
What? Okay.
This requires us to get a different set of coefficients, and let's use the notation A prime, B prime, and C prime to denote these. So again, we have 2 sets of equations. The second set of equations is the same. So it's basically just A prime plus B prime C equals 1. So it's just the coefficient of the signal. The second equation is different because before, the second term doesn't have any noise, but now the second term has some noise, and the noise magnitude is sigma 1. So basically, we just slightly change this this equation, and you get this term. And similarly, it has like 1 degree of freedom. So basically, if you set B, and then you can get A from the condition 2, and then you can get C from condition 1. So this still similarly has like 1 degree of freedom. So as a result, we basically have this type of update. So if my observation is already too noisy, I just run DDRM using like 1 set of coefficients. And if the observation is still useful, then we will do this different linear projection, which will give us a different set of coefficients. For the most trivial case, you can think of this as like just if it's just denoising, H is the identity matrix, then what my update will do is I will try to use my denoising procedure to first, at a very large noise level, gradually go to our noisy observation. And then starting from there, I run regular denoising. So in the paper, we have 2 hyperparameters called eta and eta b, and this actually corresponds to these 2 degrees of freedom, like respectively, in the paper, if you want to check all the details. Finally, let's go to the most general case, which is correspond to any linear inverse problem. So in this case, H is a general like linear matrix. Well, not all linear matrix, but most of the linear matrices are useful to us, and there are ways to compute the SVD or singular value decomposition of this. So concretely, we can decompose the H with orthogonal matrix U times the diagonal matrix sigma times orthogonal matrix V prime. And for high dimensional matrices, such as doing downsampling on images, you can actually leverage the fact that many downsampling operations and convolutional operations are kind of separable. So it means that you can do one operation on one dimension and then on the other dimension. So you can still have very efficient ways of computing these. Or at least computing products with respect to these. So now we do a change of variables. So basically, we multiply U transpose to both sides. And what we will get is like, we will get U transpose Y on the left. And then we have this, U transpose Z on the right. And U is a, orthogonal matrix. So U transpose Z is kind of like the same diagonal Gaussian. And V transpose X0 is like another transform matrix on another transform matrix vector. And the sigma is kind of like a diagonal. So you can think of it as basically, I transform this space, and my relationship between this new vector Y and the new vector X is still kind of like a diagonal relationship. So this means that the actual algorithm we do essentially performs something like denoising and depainting that we described earlier, but in this different space. So in the space of this V transpose X0. And what's notable that we have to do here is that because the singular values are not equal, so this might correspond to cases where sigma has different values in the different different rows and columns. So in this case, we have to handle the noisy cases of sigma y in like differently for each dimension, but we simply need to just handle it independently. So in the paper, we have the exact like details of the entire algorithms for this. And to show some empirical results, we compare this with other deep learning based methods. So originally, there's the original image on the top left, and the low resolution noisy input is on the second one. And our result in 20 iterations is able to generate a reasonably smooth denoised image. And on the bottom row, we have SNPs and red, which are two methods using the same denoiser, and as well as the DGP, which is a GAN-based method. So as you can see, the quality of the baselines are all pretty worse compared to what we have. And we also have empirical like numbers that supports the claims. So our method DDRM is on the bottom row, and we are comparing these metrics. So PSNR is just a peak signal to noise ratio. KID is an image distribution metric, very similar to like FID, the frictional interception distance. And NFE is basically how many iterations I need to run this algorithm before I stop. And as you can see, that our algorithm actually achieves better numbers in these metrics, as well as having much less like iterations to have. And our method basically just produces all the results that we have within 20 evaluations or 20 iterations of the diffusion model. Whereas all these prior methods using GANs or using other denoisers have to converge at a much slower fashion.
I have a question.
Yeah.
If you could go back to the beginning of this. So you use the use H somehow to split the knowledge, right?
Yes.
Like the method using explicit H information.
Yes. Okay. So every baseline is using the explicit H information, and this in super resolution is kind of a reasonable assumption because you always kind of know like in what resolution you are going to upsample to. Yeah. And here are some additional qualitative results. So notably, we have this case where we show when you have like 4x, 8x, or 16x of super resolution, and our case is able to handle both noiseless case and noisy case. And you can see in the noisy case, it's actually the image is actually very noisy, but it still recovers a reasonable human face that's relatively consistent with what we observe. Also, this is a sampling-based approach. So like in very noisy cases, you have a distribution of solutions that you can get instead of just one sample. And similarly, we have different results for different operations as well.
So there's a question online. If you go back to the previous slide.
Yeah.
Okay, so Islam asked, how scalable are these models to large-scale dense data sets? What is the time complexity and RAM use? Kind of thing.
I guess I'm not sure what dense data set means. So
maybe like very high dimensional image stuff.
Okay, yeah. I think definitely. So here we are considering the case of 256 by 256 images, and it basically like as long as we have a model for like high resolution images, then yes, I think we can run this algorithm. And the time to run this algorithm is basically 20 iterations of the diffusion model. Because we did evaluate that the matrix operations on the images basically cost nothing. And most of the time is actually spent on like doing forward propagation on the diffusion model. So I don't recall the exact numbers, but I think like depending on the network that you use, like each image should have a latency about like 5 seconds to like 20 seconds in this case. So, but I would say compared to prior work, it's much more scalable.
Okay.
Yeah.
You also need to compute the SVD, right, for each step.
Oh, so if you know the task, then you don't actually have to compute SVD. So first of all, that's something you can pre-compute. Second of all, as we just said earlier, for like many commonly used operations like convolution, you can actually do it individually on each dimension. So you have like efficient ways to compute these multiplications. So yeah, these actually cost like very little compared to running the diffusion model.
People online really want to understand the RAM usage.
Okay, so the RAM usage is basically the same amount of RAM that you would run with a regular diffusion model. So again, it depends on the architecture, but I never find it to, you can probably run like a batch size of 32 to 16 on a GPU that has 16 gigabytes of RAM or something like that. Yeah, so yeah, I think basically it does not cost more RAM than what you typically expect.
Yeah, maybe in the interest of time, let's just carry on.
Yeah, all right. So I'll go very quickly for this second part, which tries to enforce some physical constraints in motion diffusion models. So this is work done by some NVIDIA colleagues and mine. So earlier we described this DDRM procedure where we try to enforce information from the observation. And you can think of it as a projection step. So I have a hyperplane that satisfies the condition y equals h of x. And I can think of doing this update of based on y as some kind of projection step that projects the denoise output xt hat into the new result. And in this case, we're interested in can we extend the projection idea to other nonlinear problems. And so specifically, we are looking at the case of human motion. So basically, here's some results from a human motion diffusion model. And if you render it in the real world, you can actually see that this hand sinks under the ground, and sometimes the feet are above the ground. And these are not physically plausible. But we are using this projection idea. We're actually able to make the pre-trained diffusion model physically plausible without just training the model. Even though I guess I have to say this, these might not be biomechanically most efficient. So the high-level overview is quite similar. So we add after we have the result from the diffusion model, the denoise model, we basically try to do a physical projection update on this. The physical projection update basically tries to use the physics simulator and the imitation policy, and you basically try to learn an imitation policy that is as close to as your current denoise output as possible. And because you're running in a physical simulator, everything you output is physically plausible, and therefore you get this kind of a projection property. So basically, we plug in this thing into this motion diffusion model, and that's kind of how the idea works. And you can see compare some results in the same similar motions, and you can see that the baseline results are kind of floating on top of the sky, and whereas our method is actually handles the feet contact quite correctly. Yeah. So finally, I'm going to talk about this recent iClear's work on pseudo-inverse-guided diffusion models. So as I work in industry, people care more about whether it works in practice than a technical novelty. So my manager asked me, if I run the denoising diffusion restoration models on image super resolution, then what's the performance compared to if I just train a model directly for super resolution? And back then, even though we were the state of the art for plug and play method, we were not the state of the art for just compared to just training a conditional model specifically for the task. So this work tries to bridge that gap, and we actually have some results showing that you can actually bring it much higher, and you can actually using a plug and play method, you can achieve near state of the art performance compared to these domain specific diffusion models. And this is also work done by myself and some other colleagues at NVIDIA. So first, let's talk about two limitations of the DDRM. So first of all, one limitation is that it only supports linear measurements. So we need the SVD, and we have these linear combinations with everything. And the second problem is that it works very poorly for sparse measurements. So for example, on the left is the ground truth image, and we observe, let's say, 10% of the pixels as the input. Unfortunately, because the DDRM update only tries to enforce these pixels, then the sampling process is affected very poorly if you have sparse observations. And as a result, the output that you get will be look quite horrible. So one way to address this, a high-level idea to address this, is that we can try to do backpropagation through the diffusion model. So in that case, even if we change a few pixels, this backpropagation will end up affecting all the pixels, and we will try to use this backprop result for the updates. So the high-level idea is basically related to if you know about the classifier guidance or classifier free guidance, basically we try to combine the conditional score, which is the score of xt given y, with this prior diffusion model that we already have, which is connected to the score, by the way. So this is the score of p of xt, with this second term, which is the gradient of xt of log pt y given xt. So precisely speaking, this is not known in a plug and play setting. So to gain more context of it, the graphical model of this process, you can think of it as a Markov chain. So I have data, which is x naught in the middle, and on the left, I generate observation, And on the right, I can add Gaussian noise to simulate this forward diffusion process. And condition on the data, the white and xt are conditionally independent. So I can get this integral, which is y of xt, as this kind of like a marginalization over all the possible x0. However, this quantity is intractable because we have this term called the x0 conditional xt. So in some sense, if you want to get samples from this, you have to sample, like simulate the entire diffusion model. But we don't want to actually incur that cost because that would be too slow. And so even if we have y given x naught, which is like, for example, the downsampling, like likelihood and such, it's still kind of intractable. So our solution to this is that we try to approximate this with a procedure that we call a pseudo-inverse guidance. And before we get into the mathematical details, let me first show an example of how we do this procedure in practice. So, before we said that one limitation of JPEG was that it's, for DDRM was that it works only on linear, problems. Then now we are going to show like a different problem that is nonlinear or not even differentiable. So the high level idea is that, well, here the setting is that if we are given the input, which is like a JPEG encoding, how do we recover with the diffusion model? And the JPEG encode is technically not differentiable because you have quantization operations. And our goal is to start with a JPEG image that is has a lot of artifacts to get the output that looks more realistic. So basically, we want to use a property of the pseudo-inverse for matrices. And basically, for a matrix H, the pseudo-inverse of that has this property. So H times pseudo-inverse H times H equals H. So placing into the context of JPEG, you can get some Huffman encoding with a JPEG encode. But you can also give the same set of Huffman encoding by doing encode, decode, and then encode. So the reason for this is that the quantization was done once for the encode. And once you have done that, like regardless of how many times decode and encode you follow, after that, it will still be the same. So in this sense, at a high level, we can sort of say that JPEG decode is a quote pseudo-inverse of a JPEG encode. So let's first go to step by step of how the algorithm works. So first, again, we try to get a diffusion model to help us make a prediction that is denoised. And again, this model is like generic and does not depend on the problem of JPEG. The model has never seen any JPEG images. So the second step is basically we apply this degradation as well as the pseudo-inverse to the denoise prediction. So here we have the denoise result, and we apply a JPEG encode and decode, which give us an image with a lot of JPEG artifacts. So the third step is basically we want to compute the difference between the given input. So basically our input is kind of like the JPEG degraded image that we try to, get eventually. And here, obviously our output is not close enough. So we are going to compute the difference between these two, which is a vector that points us towards kind of the right direction. And how are we going to use this directly as the update? So this is actually considered like a vector, so-called vector Jacobian product. So on this vector, we have this vector that points from our current JPEG image towards the correct JPEG image. And the Jacobian is basically the Jacobian of the denoise output over the input. So basically, you try to compute the Jacobian, try to compute a vector product, Jacobian product, where the Jacobian is basically just doing backpropagation through the diffusion model. And now, after doing this additional step as a correction, we actually get something that's slightly better than what we had earlier with the first initial guess. And we can repeat this procedure to get better and better estimates that are closer to the quantum solution. And basically, if we just repeat this procedure, we will finally get the desirable output. And we can see some results on in practice, not just on super JPEG, but also on super resolution as well. So for example, here on the left column is the low resolution input. The right column is the reference. The second column is the output from a model that's specifically trained on super resolution. And on the third row is our result. And we can see that our result is actually relatively sharp, even compared to the reference. And similarly, we have results on JPEG as well, showing that on the left-hand side is the JPEG input, on the right is the reference, and on the second column is again a model that's specifically trained on JPEG. And you can see that our results are like comparable to the one trained on specifically on JPEG. It's also pretty close to the reference. Again, because this is a sampling approach, we can generate different samples from the model. And for example, in this case, we try to do in-painting tasks where we mask out the image, and you can actually get different outputs that are relatively diverse. So for example, in this bird case, the grass can appear in front or behind the bird, or in this different case where you mask out the house, you generate slightly different houses. Numerically speaking, we compare with methods that are trained specifically on particular tasks. So for example, here the gray rows are methods that are trained specifically for the super resolution task. So for example, ADM is basically trained on super resolution, but interestingly, the ADM method is only trained on this block averaging filter, which we call pool here, and it's not trained on the slightly different type of downsampling, which is a bicubic feature. And as you can see that even this very simple change of the domain shift can actually bring the performance quite worse. So in the earlier case, if you train on the exact domain, then your FID is the best. But then after you switch to a slightly different domain, the FID becomes much worse. However, our method is able to get good results regardless of the domain. And this is also similar results for in-painting. And we also have the results on super resolution, where this performs basically on par with the best method there is that's specifically trained on JPEG images. And our FID is basically around 0.5 worse, which is very small. And but we also have a better ResNet 50 accuracy in most cases. So now that we show the methods works pretty well in practice, I want to just add a little few more details on how the method is derived. So as we had earlier, we want to find good approximations to this term, which is an integral. So what we do is basically we don't know this x0 given xt term. So what we are basically trying to do is just we use a very simple Gaussian approximation. We approximate this with a Gaussian with a certain mean and a certain standard deviation. So the mean is just the output of the denoiser. So we just use the diffusion model to get this output. And the standard deviation is kind of like a hyperparameter that you can tune, or you can try to fit it with the data. But we have a standard approach to choose this hyperparameter that works in all the cases. And the second term, if you think about the earlier linear inverse problems, you can think of it basically just this is also a Gaussian distribution. So from this linear relationship, y is equal to hx plus the amount of noise. So inside this integral, both terms are Gaussian. So you can actually just come up with this Gaussian approximation for pt y given xt. And because this is Gaussian, you can basically just derive the approximations to the score in different cases. So for example, in the first case, if you have positive amount of random noise, then you would have this this quantity which has the vector and the Jacobian product through it. And if the noise is 0, then you can actually simplify it further. So basically, this term will this pseudo-inverse term will come up, and this is actually exactly the way we use to update the JPEG case. And notably, this Jacobian vector product does not require the vector to be differentiable with respect to the input. So we can just compute the vector first, and then we plug in Jacobian vector product procedure. Like in PyTorch, you can just apply autograd or VJP. And we only need the diffusion model to be differentiable with respect to the input, which it is. And finally, let me just give one slide showing how we got this other type of applications where we combine multiple inputs. So we can treat this multiple operators as a composition of simpler operators. So you have H1 up to HK, and basically, for example, here we have downsampling plus JPEG encode plus masking, and we can just approximate the pseudo-inverse by this. So we just go on the opposite direction and we apply the pseudo-inverse operations one by one. Even though this is not exact for all linear operations, we actually found that it works quite well empirically. So there are still some challenges for the current method. So this is much slower compared to the, well, relatively slower compared to the earlier DDRM method. And it's also like slightly memory inefficient due to having to back propagation through the diffusion model. And another problem is that we need a pseudo-inverse in order for this to work. And also this is relatively limited to this non-Blythe inverse problem, where we have to know what H or the forward operator is. And there are some efforts on like trying to solve these problems for like nonlinear cases or even like blind inverse problem where you don't know the operator. But I would say that these efforts on these directions don't give you like fast or robust enough algorithms. So they mostly work in cases where you have like 1,000 iterations that are pretty slow. Regardless, we have seen some works that demonstrate that diffusion models can act as very efficient priors for inverse problems. And from the results that we show here, it's much more promising to use diffusion models for these problems compared to VAEs or GANs. So yeah, these are the works and their links to the papers and codes if we have them. So yeah, thanks for your attention.
All right. So since we start a little bit late, maybe we can have like 3 to 4 minutes for questions. If you have questions now, or if people online have questions now, you can, or people online have questions, you can raise your hand, or people here just ask questions.
Rick raised hand.
Hi there. Thank you for this very nice presentation. So my question is about the generalizability of these diffusion models and inverse solving problems to non-Euclidean spaces such as graphs. Like if you, for example, transform your image and represent it as a graph, or if your data, your input data is a graphical data, like how generalizable these models to graphs, because, like, for example, GCN's graph convolution networks, they work on, we use these convolutions to learn representations of different samples in a particular data set. So each node will have its own embedding learned through the GCN. So there are so many issues with, for example, particular types of convolutions that are not scalable. And these diffusion models, they seem to be very promising and naturally extendable to GNNs. So I'm sure there should be some work on these lines, but I just want to have your insights into this.
Yeah. So I think as of now, most of the works on like diffusion models for graph data were still on mostly continuous settings. So the way people do this is that they sometimes have a predefined graph, or they have a graph-like structure, but they don't exactly try to generate the graph structure like directly. Sometimes they just generate, for example, in the molecule, they generate the location of the molecule, or in the protein case, they generate like the relative angle of the protein folding. So in this case, you don't actually generate the graph, but you like generate some continuous properties that relates to the graph. So I would say that it's still like an open problem as to how you do graph generation directly on this discrete setting. So then I guess solving inverse problem on graphs probably will rely on like better developments of graph generative models for diffusion. But nonetheless, I think if we have such a model, that we can apply methods that we discussed today perhaps for these cases, because we have seen some evidence that it works on domains other than images. So people have been using it on speech and audio. So I would say that if you have a good model for graph, then perhaps this can be done. But the problem is that we don't really have a good diffusion model that specifically generates graph structures.
Okay, thank you.
Any other questions?
So I think these diffusion models have shown very exciting results on kind of large web scale data sets. Have you seen much work on trying them on like smaller scale data sets? Like, do they work as well, or is there like a minimum data set size before you should consider using them as a generative model?
I see. I don't think there's a lot of like systematic study on this topic. Although I would, my uneducated guess on this topic would be that it probably should work as well as a GAN does in like small data set settings, because it doesn't require adversarial training, so you might not need as many regularizations to make it work. Yeah, but I don't know the actual answer to that.
I have a question about the masking problem. So in the masking problem, the H matrix is a matrix where diagonal matrix,
Yes.
where some elements in the diagonal are 0 or 1.
Yes.
So this is a matrix with determinant 0.
Yeah.
How can you compute the pseudo inverse?
So
that's my question.
Oh, I see. Well, I guess for determinant 0, you don't have to. Well, first of all, the matrix is not square. So I guess for diagonal, I would have to say it's kind of like it's a shape like this, and this is part of the diagonal. So yeah, okay. I guess in that case. So yeah, precisely speaking, like it's basically just how you decompose SVD and stuff.
I thought the image was like vectorized as a vector, and then you would have an image, the H matrix, where it was a diagonal, indicating which pixels were activated or not.
Yes, you're right.
I was wondering, like, this matrix multiplied by itself is the same, and then what is the pseudo inverse?
I see.
It doesn't have any.
I guess even in that case, you still have the pseudo-inverse. I think the pseudo-inverse would be just itself. So like that type of matrix.
Well, if you have H times H transposed, it would be H, and then if you take the inverse of that, you cannot compute it because the determinant is 0. Well, I don't know.
Oh, I see. Yeah, you're right. So yes, then I would say that it should be like a full rank in rows. Okay. So I guess So the matrix is something more like this. So I need to revisit that part of zeroing out. So it's more like you don't have the dimension. So effectively, like you're multiplying 0 with that. Yep.
Okay. Any further questions?
Yes.
So I'm just curious, like how robust you are, like if you're denoising when they are bumping shapes in terms of image semantics.
We haven't tried that. Although I guess the hope for developing these methods is that we want to leverage, these very large scale models trained on a lot of data, such as stable diffusion, to hopefully we have models that covers like everything. So hopefully we don't have to get through this domain shift problem. That being said, in other domains, for example, like medical imaging, there definitely going to be some type of domain shift, and I guess it depends on the case. So if the domain shift is so large that even your like prior model thinks that the new samples have like very low likelihood, then there's no way that like a Bayesian method will work, because in that case, like your prior just is not a good prior. But if you have domain shifts in the sense that you shift the domain, but you still have like the data in the new domain, so you can probably use that data aggregated to train like the prior. So I think it depends on having a good prior. That's possibly with domain shift you can train on like more data that are not necessarily labeled, because like if you had just labeled data, then you don't need this type of approach. Yeah.
All right. So I think that's it for today. So thanks everyone for coming, and let's thank the speaker again.
Yeah, thank you.